everyone. My name is Braet, and I'm an Erasmus student from Ghent University, Belgium. And I'm studying at the moment at Brno University of Technology, where I'm doing my thesis about nonlinear numerical study of stainless steel IPE80 profile for a fatigue experiment. My supervisors on this research are Petr Miarka and Professor Stanislav Seitl. First, I will give a little introduction, then I will show the numerical model for the experiment and with the different stiffener options, and then of course I will show the results. As you can see, this research is framed in a larger picture of the stainless steel used in the bridge structures. The motivation for this research is that the SN curve is usually measured on round specimens, as you can see on the right. But we want a comparison between the SN curves for round specimens and IPE80 profiles. The stresses in the 3-point bending test for option 0, that is without stiffeners, and S2W equal 10, as required for the setup of the experiment. The desired stress needs to be lower than 350 megapascals at the bottom of the profile, but the max deformation of the machine is 6 millimeters, so actually an S2W equals to 3 is required. S2W equals 10, therefore the length of the profile is too large to perform the experiment with the machine, because the deformation will be larger than 6 millimeters. That's why we use S2W equal to 3 and a deformation of 4 millimeters. For obtaining the desired stresses, the use of stiffeners is justified. Here on the right you can see the IPE80 profile in stainless steel, which is used in the experiment. And only 1/4 of the profile will be modeled because of symmetry in 2 directions. Normally, there's an expected crack, but it didn't occur in the experiment. That's why the research focuses now on the plastic yielding, the buckling, and the bending, etc. In this research, we investigate the influence of different stiffener options on the stress and buckling, and etc. Therefore, we're creating the later experiment based on this parametric study. Here you can see the stiffener options which will be used in this research. At the right you see the IPE80 profile in the standard version, so without stiffeners. Then the option 1, only full stiffener at the middle. Option 2, only full stiffeners at the end. Option 3, full stiffeners at the middle and at the end. Here you can see option 4 with a half stiffener at the middle and full stiffeners at the end. Option 5 is the same, but with a triangle shaped stiffener in the middle. And option 6 is with full stiffeners at 1/5 from the middle and full stiffeners at the end. Here you can see the material curve for stainless steel. 2 specimens will be used in this research. Here you can see the characteristics of these specimens. And at the right you can see the formulas which are used for obtaining the graphs. In this graph you can see the stress-strain curve for specimen 1 and for specimen 2. Here you can see a validation for a correct material input. On the left you see the graph for the force on deformation. And in this graph you can see the curve for option 0, which corresponds with experimental curve 2, and option 0 adapted, which corresponds with experimental curve 1. In the table below you can see the characteristics for specimen 1 and 2, and the colors blue and yellow, orange and gray correspond with the correct curve. At the comparison table at the right you can see the deformation at point UZ 0.6, that's equal to time 1.15 seconds. And you can see that the forces at this point are very close to each other for option 0 and experimental 2, and for option 0 adapted and experimental 1. Now for every option from option 0 to 6, I will show the deformed shape, the von Mises stress, an animation for the von Mises stress, the height versus the stresses in the graph, and the force vs deformation in the graph. Also comparison for all options, for stress SYY, for stress von Mises, and for force deformation graphs. In here you can see the deformed shape for option 0 to 6 in a 3-point bending test with a deformation of 4 millimeters. Here you can see the von Mises stress for option 0 to 6 in a 3-point bending test and with a deformation of 4 millimeters. Here you can see an animation of the von Mises stress for option 0 to 6 for a 3-point bending test and a deformation of 4 millimeters. You can see the gradual development of the von Mises stress throughout the profile. Here you can see the height versus the stress graphs for option 0 to 6 in a 3-point bending test and a deformation of 4 millimeters. And here you see a comparison for the SYY stress, for the von Mises stress, and for the force vs deformation comparisons for a value of S to W equal to 3 for the options 0 to 6. And as you can see, option 3 has the highest reaction forces and option 0 the lowest. For option 4 and 5, the curve is exactly the same, so there's no difference between the triangle shape and the rectangular shape. Option 2 and option 6 only give a little increment of the reaction forces, so that's not very important. The aim is to come closer to the Euler-Bernoulli beam theory, so the linear elastic stress distribution will be used for the fatigue. And in extension of this research, a 3-point bending test for option 0 and with the parameter S to W with the values 3, 4, 6, 8 and 10 will be investigated, and the same accounts for a 4-point bending test with the same values of S divided by W. Also, a 4-point bending test will be investigated with full stiffeners at the load. And I will show the deformed shape, the von Mises stress, and the height versus stress and the force vs deformation graphs. Here you can see the von Mises animations, so the von Mises stress and the gradual development of this stress throughout the profile with different values of S divided by W from 3, 4, 6, 8 and 10. This is for a 3-point bending test in option 0, so without stiffeners and a U max of 4 millimeters. Here you can see a comparison graph for the stress SYY, the von Mises stress and the force on deformation graphs for the different values of S divided by W, 3, 4, 6, 8 and 10. As you can see, the force deformation graph for S divided by W10 has the lowest reaction forces, and for S divided by W6 has the highest reaction forces. The stresses are also the lowest with the highest value of S divided by W. Here you can see the von Mises animation for the von Mises stress in option 0 with the S divided by W for values 3, 4, 6, 8 and 10, and also option 1, so with the stiffeners under the load with S divided by W3. This is for a 4-point bending test and the deformation U max is 4 millimeters. Here you can see the comparison graphs for SYY, von Mises, and the force deformation graphs again. The same trend accounts here for the 3-point bending as for the 4-point bending test. An extension of this research, comparison graphs are made in a 3-point bending test with S to W equal to 3 for option 3, 4 and 7. So that's with a full stiffener in the middle, a half stiffener, and a 3/4 of a stiffener in the middle. And this for thicknesses T equal to 4, 5, 6, 7.2 or 10 millimeter thickness of the middle stiffener. And I will show the von Mises animations. Here you can see the von Mises animations for thickness 4, 5, 6, 7.2 and 10 millimeters for option 3 with a deformation of maximum 4 millimeters. Here again the von Mises animations for option 4 with the deformation of maximum 4 millimeters for the 5 thicknesses of the middle stiffener. And here again the same von Mises animations for the 5 thicknesses for option 7 and a deformation of maximum 4 millimeters. And here you can see the comparison graphs for the stress SYY von Mises and the force deformation comparisons for option 3 as divided by W3. As you can see, for the reaction forces, the thickness T of 10 millimeters has the highest reaction forces, and this decreases with the decreasing thickness T. The stress SYY and the von Mises stress are the lowest for the highest thickness of T. You can see the same trend in the comparison graphs SYY, von Mises, and force deformation in option 4 as well. And the same accounts for the comparison graphs in option 7. It has the same trend. Now, in extension of the research, the 3-point bending test for S divided by W free, option 3, 4, and 7, so with full, half, and 3/4 stiffener in the middle, will be examined for a deformation UZ equal to 0.6, 1, 2, 3, and 4 millimeters. Here you can see comparison graphs for the SYY stresses and for the von Mises stresses for option 3, 4, and 7 at the difference values of the deformation. As you can see, a lower value for deformation UZ gives lower stresses as well. Here you can see the force vs deformation comparison for option 3, 4, and 7. And also at the right graph you can see again the force deformation for graphs for option 0 with the different specimen values. In the table below you can see comparison for deformation at point UZ is equal to 0.6 millimeters between option 3, 4, and 7, and this at time 1.15 seconds. And you can see the forces, the stresses, SYY and von Mises stress in top and bottom. You can see the values of these stresses and forces. Then an extension of the research for the same three options again. Now the deformation UZ at points 0.6, 2, and 4 millimeters. I will show a relative comparison for the SY stress and the von Mises stress. Here you can see the relative comparison graphs for stress SYY and von Mises stress for option 3, 4, and 7, and this at points UZ equal to 0.6, 2, and 4 millimeters. You can see the relative comparison because the stiffener length is in the relative coordinates from 0 to 1. Now in extension of the research, the same deformation steps 0.6, 2, and 4 millimeters will be examined for option 0 for both specimen input values. Here you can see the comparison graphs for stress SYY and the von Mises stress at points UZ is equal to 0.6, 2, and 4 millimeters, and this for specimen 1 and 2. And at the right you can see the comparison between these. As you can see, the stresses for specimen 2 are lower for the SY stress and von Mises stress as well. They're lower than for specimen 1. I hope everything was clear, and I want to thank you for your attention.